Hello everyone, my name is Yogesh and this is our presentation for final project for EECS-4401 Artificial Intelligence. Our project is titled Z3 SMT Solver Evaluation and was completed by my team members Divyansh and Veerman Singh Kalra. In this presentation, we will demonstrate how we use the Z3 SMT Solver to solve three very different types of AI constraint problems: Sudoku, Cryptarithms, and job scheduling. Now, I'm going to go over the motivation and objectives. So, the motivation behind this project comes from the importance of constraint based reasoning in AI. Many AI tasks, such as planning, scheduling, verification, and puzzle solving, can be expressed as constraints. SMT solvers like Z3 are extremely powerful because they can reason over both logical and mathematical constraints at the same time. So our objective was simple: demonstrate how SMT solving works, show how Z3 handles different problem types like numeric, symbolic, and scheduling tasks, and evaluate how efficiently and accurately Z3 solves them using the same unified solver framework. Now, I'm going to go over quickly what is an SMT solver. SMT stands for Satisfiability Modulo Theories. An SMT solver checks whether a given logical formula is satisfiable under theories like arithmetic arrays or strings. In comparison, SAT solvers only deal with Boolean variables. CSP systems handle constraints but don't use formal logic. So SMT sits right in the middle, being more expressive than SAT but more structured and powerful than general CSPs. We choose Z3 because it is extremely fast, well documented, open source, and has a clean Python API, making it ideal for real AI tasks. Now, I'm going to quickly go over the system overview. So, our system is implemented entirely in Python and it contains three solver modules: Sudoku solver, Cryptarithm solver, and scheduling solver. Each module builds a Z3 model, solves the constraints, prints the solution, and also outputs the runtime so we can evaluate the solution on different inputs. So we also included a full automated test suite for validation. The only installation requirement is you need to have a Python in your system and install the Z3 solver using pip install. Now I'm gonna give the presentation command to my teammate Veerman, and he's gonna go over the next of the slides. Thank you.
So thank you, Yogesh. So how to use the system? To run the system, you simply navigate into the project folder and run the solver of your choice. For example, here we have three solvers. First is Python Sudoku Solver PY, and the second is Cryptarithmetic Solver PY, and the third is Scheduling Solver.py. And we can also run the test suites like test Sudoku, test Cryptarithmetic, and test Scheduling. Everything runs out of the box, so we do not require any extra configuration or datasets. So next, we will see over Sudoku solver problem description. So our first example we choose is Sudoku, which is a structured 9 into 9 constraint satisfaction problem. Each row, column, and 3 into 3 block must contain digits 1 to 9 exactly once. In our model, we create 81 integer variables, one for each cell, and we enforce the digit range from 1 to 9, like in normal Sudoku. So we apply Z3's distinct constraint for rows, columns, and blocks, and then we encode the fixed clues taken from the puzzle input. This creates a clean mathematical representation of the Sudoku rules. And now we go over the benchmark results of our first Sudoku solver. We evaluated Sudoku puzzles at four difficulty levels: easy, medium, hard, and minimal clue puzzles. The results were consistent. Puzzles with more clues solved instantly. Puzzle with fewer clues took slightly longer but still completed in under a second. This demonstrates that Z3 handles combinatorial CSPs extremely efficiently, even with very large search spaces. So next will be our cryptarithmetic solver. Our second example is cryptarithmetic, where letters represent digits. We evaluated two puzzles, including the classic 10 plus more is equal to money, So in the Z3 model, each letter becomes an integer variable. All digits must be unique. Leading letters cannot be zero. And we encode the full arithmetic equation. Z3 finds the classical solution almost instantly. For the second puzzle, base plus ball is equal to James. Z3 correctly determines that the puzzle is unsatisfiable, demonstrating its ability to detect no solution cases. Now I'm going to pass my presentation to my teammate Divyansh.
Thank you, Virman. So we'll go over the third example, which is scheduling problem. So this is a real world scheduling problem. We assign employees to shifts while respecting constraints such as no two employees working the same shift, availability restrictions, and gender-based requirements in the harder example. Again, each shift is modeled as an integer variable, and we use a distinct constraint to avoid duplicates. These types of problems are common in planning and operational research, and Z3 is very well suited for them. Now we'll study the benchmark results when we run the scheduling problem. So we created two scenarios. The one scenario was very simple, uh, as it has three employees and comparatively less constraints. And in our second example, we uses four employees with more restrictions. And as you can see, Z3 still generates a correct schedule correctly in both the cases. But the running time can vary because it depends on the number of constraints we use in each of the problem. So now we'll see the testing and validation. So we use various test cases to test our problems, whether it matches the correctness of the solution or not. So Sudoku tests checks row uniqueness, column uniqueness, block uniqueness, and others. And similarly, the Cryptarithm tests digit uniqueness, non-zero leading letters, etc. And similarly for the next scheduling problem. So all these tests are included in our code files as well. So finally, to conclude this project demonstrates the power and flexibility of Z3 SMT Solver for solving a wide variety of AI constraints. Using the same solver engine, we are able to solve a numerical puzzle, symbolic arithmetic puzzle, and practical assignment challenges. Thank you very much for this presentation. Now we can quickly go over the quick demo of our project. So this is a whole project that we built, and to run the solver, we can write these commands. So if we enter this, it will run the Sudoku solver. So as you can see, it has taken three examples: easy, medium, and hard. So this was the original problem, and it solved it. And at the end, you see the benchmarks like for easy, medium, and hard. And similarly, you can run for the other two problems, and you can see the results. Thank you very much.